All right, thank you. So yesterday, we discussed near-inertial waves in the ocean. So the model was a shallow upper layer in a two-layer model. And we said that following an atmospheric storm, there would be an initial condition which is uniform velocity in the upper layer. And the subsequent motion would be waves, near-inertial waves, oscillating at the inertial frequency. But when there is a background flow, a steady background geostrophic flow, these waves will be distorted. And so this complex amplitude of the wave field will require some structure in the horizontal plane. And it will follow this Young-Bengel equation, where you have advection by the background flow, refraction due to the vorticity of the background flow, and some dispersion, which is the next order in the dispersion relation of near-inertial waves. Okay, we saw that this equation is a Schrödinger equation, right? And that the Hamiltonian is the Hamiltonian of a particle in a steady electromagnetic field. And the vector potential was minus u, the velocity of the background flow, and the electric potential was 1/2 of the vorticity of the background flow, minus the kinetic energy of the background flow, more or less. Okay, and so the goal was, starting from this uniform initial condition, we'd like to predict the long-term statistics of M, maybe time average statistics. And so we're considered that in a first limit, which is when the background flow is weak. Okay, so psi we wrote as gamma times chi, a normalized version of the stream function, and then gamma is the strength of the background flow in terms of the strength of the stream function. Okay, the equation looks like this with gamma here and gamma here. And the first thing to look at, maybe the simplest thing, is weak gamma. When gamma is very small, you can see you have the free particle Schrödinger equation, and then a weak potential that perturbs it, and that's the typical situation that we're used to in asymptotics or quantum mechanics, maybe. And so we made various predictions. We predicted that the modulation of the wave kinetic energy, which is just the modulus of m squared, would be a constant. So m squared would be the constant initial value plus a modulation proportional to the stream function. And so here I showed the time-averaged wave kinetic energy from numerical simulations, and this is here 1 plus 2 psi, so the prediction. And there was good agreement because gamma is small and we're in the perturbative regime. We can see that this distribution is indeed the stream function, so it's not exactly the vorticity of the background flow. So there are claims or hope that maybe m squared will be strongly correlated with the vorticity, but that depends what the flow looks like. If it has a single wave number, then yes, the stream function looks very much like the vorticity, but if it's multi-scale, no, and in that case, it's quite different from the vorticity field, which has more localized patches in the anticyclones and cyclones. We looked at the gradient of m modulus squared. This is the potential energy of the waves. We got a different prediction. This one was predicted to be proportional to the kinetic energy of the background flow. I think twice, maybe this, I don't remember the prefactor. But again, you can compute that prefactor and you get good agreement between the prediction and the numerical results. And we looked at the Stokes drift, which was predicted to be minus u over 2, velocity of the background flow over 2. And you can see that there's a good agreement here in this prediction for the time average Stokes drift when compared to the numerics. Yes?
On these results from last time, so you mentioned that the earlier work sort of said, oh, anticyclones should be attractive. And then you have this extended quantum mechanics analogy where you ask, so it's not really the vorticity minus kinetic energy.
Yes.
So does that give a better fit? Let's see the picture of that.
Okay, so that's, yeah, very good question. Indeed, so this is the potential now in this analogy that includes all the terms. I'm considering small gamma, so this one in this limit, this one is of order gamma, and this one is quadratic in a stream function, so it's of order gamma squared, which means that in this limit, this term is negligible, so the potential would be only Laplacian sign, okay? And yet, the distribution is not exactly given by, attraction in the potential minima. And in fact, that brings me to, what we're going to do now. So now we're going to consider the opposite limit of large gamma. To some extent, it looks maybe more challenging because then it becomes, advection by a strong background flow. Okay, so this looks like advection diffusion is replaced by dispersion, and that's what's going to save us, basically. But otherwise, you know, if gamma is really large, gamma looks like a Peclet number, maybe, and so that would be a very large Peclet number limit if you think this behaves maybe somewhat like a passive scalar. Okay, and so in this limit also, this potential will be very different, because now we're considering gamma much greater than 1, so this would be the strong advection limit. And now the potential V is dominated by this term. So V of x is approximately minus u squared over 2. Okay, so if the particles are attracted by the minima of the potential, the particles should end up, going to put that between quotes, end up in fast flow regions. Okay, where u squared is large and hence the potential is small. However, you could also question that argument that the particles should end up in the potential minima, because that's really a picture that holds for a damped particle, right? Here, particle on a potential hill, then it's going to fall, you know, in the potential well, and it's damped and it's going to end up in the potential well. But for a conservative particle, it's not quite the case, actually. If you have a particle that's on top of a potential hill and there's a well, I know the particle has very small initial velocity here, it's going to fall inside the well, yes, but it's going to come back up, and in fact, it's going to spend very little time in the well. Okay, so it's not obvious at all that accumulation of particles should be in the minima of the potential on time average. Okay, and in fact, so at this stage, when you look at the YBJ equation, it's maybe not obvious how to make predictions in that limit. But another thing we said is that this YBJ equation is exactly analogous to this quantum mechanical problem. And now gamma going to infinity is when, if I divide by gamma, I can get rid of this term, or this term becomes small. Okay, I cannot quite get rid of this term. But this is the limit h bar going to 0 of quantum mechanics, right? You'd have 1 over gamma here, which is where you have an h bar, and you have 1 over gamma here, where you also get some h bar. Okay, so we also know it's the classical limit of this quantum problem. And so another way to determine the statistics of this system in the large gamma limit is to invoke the statistical mechanics of classical systems. And that's how we're going to make predictions for the Young-Benjelloul equation in this limit. Okay, does that make sense?
So you don't mean classical limit in the sense of semi-classical limit of type wave number asymptotic?
That's what I mean, yeah. Yeah, yeah. So this is also, okay, so this is the classical mechanics limit. And also, of course, in this context, this is also when you would use the WKB method, and this is also the ray tracing limit. Okay, where you would look at the trajectories of small wave packets. So in fact, what happens in this classical limit is that you would describe the field as a collection of small wave packets. Okay, so you have a small wave packet here with a position x of t and a wave number here, maybe p of t. Okay, and these wave packets, they would be the classical particles of classical mechanics. Okay, so the revolution equations are just the Hamilton equations for this Hamiltonian here, but we have that's equivalent to the YBJ equation. So x dot will be dh dp. Well, this is to be understood component-wise, and p dot is minus dh dx. Okay, so that's equivalent to Newton's third law, but the starting point of equilibrium statistical mechanics is this Hamiltonian point of view. Okay, then there's the Liouville theorem. And basically what this says is that if I consider the phase space xk, okay, here it's 2D, so it's 4-dimensional, x, y, kx, ky. And then here the volume, I'm not sure how to write this. The volume in phase space is conserved. And what I mean by that is if in this 4-dimensional space you consider a cloud of neighboring initial conditions, right? This cloud will be deformed by the flow here, but this flow is divergence-free in phase space, right? The divergence would be dx of this plus dp of that would be 0. So the flow is non-divergent, so this cloud of initial condition is going to deform as it evolves due to the dynamics in phase space, but it will keep the same volume. Okay? So now particles, I'm going to consider particles with initial energy E0. So that's the initial value of the Hamiltonian locally for that particle. And this value is conserved. And so these particles, they only have access to a hypersurface of the phase space, which is when the Hamiltonian is equal to E0. Okay? They have access to a hypersurface h of xp equals E0 in phase space. And now what we're going to say is that, probably this flow in 4-dimensional space is chaotic. And so what happens is that on this hypersurface, this cloud of initial condition, which you can consider as a patch of dye, it will be distorted by the chaotic flow and it will be homogenized, and eventually it will be uniformly spread over this hypersurface. Okay? And that's the ergodic assumption. And that's an assumption here. Okay, so how should I say this? Basically, all the points on this hypersurface not sure how to say that, are visited at the same frequency, maybe, on time average. Okay, so the measure for the density of particles in phase space, the time average measure will be uniform over this hypersurface. Okay? So basically, we're going to replace long time averages. That's the recipe now. Long time averages by averages in phase space. Using a density in phase space that would be some rho of xp. It's a constant, and then it's uniform on the hypersurface where h of xp is equal to E0. Okay? So we can see how, what kind of predictions we get with that recipe. And so for instance, we can just look for the time average of m squared at some position x0. Okay, so remember m is the wave function. So the time average of m squared is the probability that the particle is at x0 regardless of its momentum. Okay? It's probability. Not sure probability is the right thing, but you get the idea. To find the particle at x0 regardless of its momentum. Okay, so in phase space, using this recipe, we're going to integrate over x and k. Sorry, momentum is p, but it turns out to be the wave number, so sometimes I get confused between p and k. But here it's momentum p. So dx dp, and then the particle, the event that we're interested in is the particle being at x0, and then we have this probability density delta of h of xp minus E0. Okay? So let me substitute. We integrate over x. That's c. There's a delta of, going to expand the Hamiltonian over there. So that's 1/2 p plus u squared plus v of x u of x0 plus v of x0 dk, dp, sorry, and p is in r squared here, I'm going to say more or less. We're going to change variable to capital P here. Okay, capital P is p plus u of x0. Okay, so that's c, the integral of delta of capital P squared over 2 plus v of x0, and dp is now d capital P, which I'm going to write in polar coordinates 2 pi p dp. Okay, and p dp is dp squared over 2. So here that's p going from 0 to infinity. So this is 2 pi c times the integral I'm going to call s equals pi squared over 2. That's the integral of delta. Sorry. I'm missing the minus E0 here. Okay, so delta of S minus E0 minus V of X0 ds, and S goes from 0 to infinity. Okay. And this basically is going to be 1 if this quantity is positive, because I'm integrating over positive values, and 0 otherwise. So it's going to be a Heaviside function of E0 minus V of X0. Okay? So now we have to estimate what is the typical value of E0 for those particles. Okay, so the initial energy so at t equals 0, the field is homogeneous. So we're going to say that the momentum at t equals 0 is 0. And if we substitute in the expression of the Hamiltonian here, we just get u squared over 2, cancels out with this one, and we have Laplacian psi over 2. Okay, so E0 is Laplacian psi over 2, evaluated at x of t equals 0. So for a given particle, its initial energy, it's half the vorticity at the initial location of the particles. And basically this quantity here, it's of order gamma, whereas the potential here, V of x0, is of order gamma squared. Right? It's dominated by this. So we're going to say that E0 minus V of x, that's order gamma, that's approximately equal to the dominant term of V, which is simply u squared over 2. There's an x0 here. Okay, and that's of order gamma squared. Okay, and that's a positive quantity. So you see, I'm going to say, well, this is always a positive quantity, so this h is 1 almost everywhere. Of course, at some point we're going to have to discuss this, because if I look at the precise locations where u squared vanishes, then I have to do something, I have to refine this argument. But providing u squared does not vanish at the location of interest for large enough gamma, this is going to be 1. Okay, so this quantity here, that's a weird thing to write, but we're going to say it's approximately 1, meaning it's 1 almost everywhere, in fact. Okay? Yep?
Just a comment, this is great. I mean, the hypersurface is not visited to the same frequency. That's the whole magic, right? That's what we said earlier, the velocity is non-uniform. So the delta function looks harmless, but it's actually a non-uniform rate of the energy. Precisely gives you the speed at which the particle will pass through the particular location on the hypersurface. It all corrects itself, but it's not a it's just a detail, but it's not a uniform measure. That makes it interesting. But yeah, it's different.
Well, the velocity in physical space is non-uniform. You can see. The velocity in phase space is non-uniform but divergence-free, so statistical mechanics tells you you're going to be uniformly distributed over this hypersurface. So yes, I insist that you may believe that the ergodic assumption holds or not, and I think it's a whole field in math to show when this assumption will hold. But then if it does, standard microcanonical statistical mechanics is that basically all these states are the microstates of the system, and so they're all going to be visited with the same probability, and that's this statement here.
You can use a simple pendulum and get the wrong answer. Anyhow.
Well, maybe a simple pendulum is not ergodic, probably. It's 1D, it's the flow cannot be chaotic, so yeah.
A very silly question, maybe, because I didn't understand what you are trying to compute. So this bar is for the time averaging.
Oh, this bar is a time average, I'm sorry. Yes.
And then can you explain why you try to compute this time average? Because the original problem was a dynamical problem, right?
Yes, so the problem is a dynamical problem, but basically I would like to know where the kinetic energy of the wave will be predominantly located on time average. So I'm computing the time average because in the long time, what I get is that it's going to be uniformly distributed here. Yes.
Which is the consequence of this time average.
That's a consequence of this, yes. I mean, if it looks trivial, I'm happy. That's not what, the belief is that the particles should end up in anticyclones. There are other arguments telling you that most of the particles should end up in anticyclones. Here, indeed, that's not what we get. What we obtain is that the distribution of particles should be almost uniform. Well, uniform according to this computation.
But this don't tell you whether you really have to say, when you say that the anticyclones, they will stay forever at the same place, right?
Yes, the background flow is steady. Yes. So it's not the usual where, for instance, we don't average over realizations of a background flow, something like that. The background flow is fixed, and you want to know what will be the time average distribution of wave kinetic energy. Okay, and the answer, according to this computation, is that it should be uniform. Okay?
Somehow you can have much more information from this classical approximation. So it really gives you something which is enough information.
Yeah, maybe, but you know, we got to start somewhere. I mean, at this stage, I don't think no one has ever used statistical mechanics just to solve this problem. So I'm going to start with the time averages.
And maybe the last question. So the assumption on the initial data, because of course, if you put all the particles initially at the same space, I guess you will not get this separation, right?
Well, there's a trick here, which I think is maybe a bit confusing, but in fact, having many particles or a single one is the same thing because the equation is linear.
Yes.
So I guess if I have a single particle starting at a given location, probably will move around in phase space and eventually sample the whole, or this whole hypersurface with uniform probability on time average.
Did you assume here that all the inertial surfaces, they cross all the positions?
Sorry.
E0 is an inertial surface in the phase space.
Yes?
You assume that the projection of this inertial surface for each energy level is the whole spatial case?
Here, yes. Yes, that's what I'm, basically the particles will be able to reach. Well, that's what I'm claiming here, that the particles will be able to sample the entire spatial domain. Well, or not. So here, okay, so that's when we're going to refine that almost everywhere. Now, if U squared is 0, then, you know, we have to refine this argument, and there are regions where you will have depletions of particles, in fact, where U squared is exactly 0, or very close to 0. Should I?
There cannot be somehow, say, in a small part of the domain.
Sorry, say again?
Somehow, what you put here or what you assume that
I'm not, yeah.
that's what is not clear to me is that the particles, they cannot stay in a small part of the domain.
Most of them cannot, no. Okay, and then we're going to discuss, maybe when I compare predictions to the numerics, I'll be able to explain more clearly or illustrate more clearly what happens. Hopefully. I'm gonna, yeah, okay. That's okay, I'm gonna carry on. So we get a uniform probability 2 pi c. Now, going to continue here maybe. Remember that the action is conserved, so the space average of m squared, which I can time average as well, this has to be 1, but this has to be 1 at any time, in fact. So this 2 pi c must be equal to 1. Okay, and so c, this normalization constant, is just 1 over 2 pi. Okay, and the prediction is, so we simply get m squared average at location x is 1. Okay, uniform distribution, spatial distributions of the particle according to this maybe naive application of statistical mechanics. Okay. I'm going to compute maybe one other example. I'm going to compute the time average of the potential energy of the waves, which would be this quantity, the gradient of m squared, time average at position x0. Okay, I want to compute that quantity. You remember from the quantum analogy, this is also minus I grad m squared, and minus I grad m is the momentum. Okay, so this thing here is just p squared. Okay, so now the classical equivalent of that in the classical limit is now I want to know the time average of p squared. And so this quantity here, grad m squared average at some x0, I will say that it's the average in phase space, delta of x minus x0, looking at position x0. I want the average of p squared, and then I multiply by this density here where c is 1 over 2 pi. 2 pi delta of h minus E0. Okay, dx, dp. So this is 1 over 2 pi, integrating over x. I have p squared delta of, what was it, 1/2 p plus u of x0 squared plus v of x0 minus E0. dp. Again, I'm going to change variables to this capital P here. So it's 1 over 2 pi. The integral little p is capital P minus u squared. And then I have delta of p squared over 2 plus v of x0 minus E0. And this is just function of, well, no, I'm going to keep d capital P here. I'm going to expand the square here. So it's p squared minus 2. There was a 1/2 here that I forgot. There was no 1/2 here, apologies. So p squared minus 2p dot u plus u squared. Okay, this cross term here is odd in p, so the integral will be 0. That's odd in the components of p. Okay. So I'm left with two integrals. I have u squared delta, the same delta as before, I think. E0, 2 pi p dp, that's the first one. And the second one is the integral with the capital P squared. Delta of the same thing. Okay, so this one here is the same Dirac as here, so we could change variable to s, we would get the same Heaviside function. And so this one will simply be u squared. Okay, so this whole thing is just u squared of x0. And here, I'm going to do the same thing. I'm going to say that this is d of p squared over 2, which I will call s. I've got s here. This one here would be 2s. Okay, and if I'm not mistaken, I should get okay, let me do that. So this one will be twice the integral of S delta of S plus and V of x0 minus E0 to lowest order is just minus 1/2 of U squared of x0. Then there's a small order gamma term, but this one is of order gamma squared. That's this. And then ds. Okay, so S is just going to be U squared over 2, and I get twice this. So this quantity here will be another U squared of x0. And so finally, I obtain that grad m squared average, this potential energy at location x0, is twice the kinetic energy at x0. Okay, so here is a prediction that's maybe non-trivial. As a remark, I'll show one last prediction maybe. I mentioned the Stokes drift. Those of you who know what that is, so even though the velocity field is the Eulerian flow is mean zero in time for a given wave. If the waves are structured, there can be a mean drift, mean Lagrangian drift. And this drift is called the Stokes drift. And here, I gave the expression for the Stokes drift. It's quadratic in M. You can compute it using the same trick here. And you get that at location x0, this will be minus U of x0 over 2. Okay, so that's another prediction we can compare to numerics. Okay, does that make sense? So, I agree, maybe we could predict a lot more, but at this stage, I don't think people have used that approach to try to compute the statistics in the system. So, let's start with first things first. Okay, anything else I want to say? I think that's good. So again, we can compare that to the numerics. So now we're running numerical simulations with a high value of gamma. Try to understand this limit. That's the strong advection regime. So gamma is 30. And you can see here the prediction for the potential energy. Okay, that's twice the kinetic energy of the background flow. And now maybe it depends if you're a physicist or a mathematician or a friend or not a friend. But I think this works pretty well. Like you see, all the same structures.
What's contour and what's color?
Why is this? This is what's being colored. And the contours are, I think there are contours of the same quantity with the same levels for the two plots, but I wouldn't be able to give you the exact value of the levels. Okay, so we're showing both ISO values and contours, but it's redundant to some extent. And so what you can see is that, quantitatively it seems to be right. We get the right structures at the right locations with the right magnitude. So I would say I would claim this is success. Now, of course, you can also see that there is some granularity of the numerical results here. And this granularity to some extent seems to be unavoidable as just, I think it's a feature of a field I don't quite know, which is quantum chaos, where if you look at the eigenmodes of this system at very small scale, they will have this granularity. And so it's some kind of an interference pattern of all these modes. And so I would claim if you smooth that over a typical wavelength, then this would disappear. Or maybe even if the flow were slightly time dependent, maybe you would disrupt that interference pattern. But I'm not entirely sure. And I believe there are, if you look up the literature on quantum chaos, there are probably scaling laws for these fluctuations. Okay, yeah?
Here the numerical simulation
YBJ with uniform m equals 1 initial condition. With a fixed background flow, time independent, yes. I'm using the same background flow that I showed you before for all the numerical simulations. But I went from low gamma to high gamma, and I claim that this statistical mechanics prediction seems pretty good. You can see the potential energy of the wave does accumulate in fast flow regions, okay, not in anticyclones or cyclones. I think,
So this is an actual time average of the simulation.
That's right.
If you just look at a snapshot, will it look similar, or will it?
A single snapshot in the long time? I don't know. Probably more. We're probably smoothing out some fluctuations here, I would assume. I don't have a snapshot at hand.
That's the next thing, to compute all the fluctuations.
Yes. Yeah. We probably could. Yeah. So that's the wave potential energy. We can look at the Stokes drift. Okay. Again, this is the prediction. And the color bar means something, like it's the actual quantitative predictions. So you can see again, the pattern is exactly the same. The structures seem to be the same, but there is again this granularity of the numerical results, which are, I think, some signature of quantum chaos that you could smooth out. Once the de Broglie wavelength maybe becomes incredibly small, then maybe you could smooth out your results depending on what you're interested in. Okay, so that seems pretty good. If we now look at the wave kinetic energy, just m squared, well, here it's a bit more debatable, right? The prediction was that it should be uniform and it should be equal to 1. So that would be the white level here. So here you could say, well, okay, the granularity is a bit strong, but indeed, if you smoothed out over a small wavelength, over a small scale, you would probably get a uniform background with value 1. But then there are also clear failures of this prediction that it should be exactly 1. And these are the blue spots here, which corresponds to deficits in kinetic energy. And maybe these two bright red spots, which correspond to accumulation of wave energy. And these are in anticyclones, and these are in regions where u squared equals 0, while the velocity vanishes. Okay, and so basically, I think during the discussion, we got the ingredients of what's going on here. These regions here where u squared equals 0 are regions where we should refine our arguments that everything's dominated by u squared, because precisely it vanishes in those regions. So we said almost everywhere. Well, here is the signature almost everywhere. So that's one thing to correct for. And in fact, you can take that into account. So we went back to this ergodic prediction here, but we took into account the actual distribution of E0, which would be the distribution of the vorticity of the background flow. And if you know the PDF of zeta, which you know because you prescribe the background flow, then you can take into account all the distribution, the narrow distribution in E0, and in fact, you can compute these blue regions here. So they're fully compatible with the ergodic prediction. You just have to be a bit more careful about just claiming that some Heaviside function is approximately equals to 1, which doesn't mean anything. So this we can take into account using the ergodic assumption. Now these here are a bit different. The red spots where you have accumulation of wave energy, they're in anticyclones, so fully compatible with the general belief and the arguments of Danu, Van Essen, and Buehler. It's a very small fraction of the overall kinetic energy, but in fact what happens here is that it's kinetic energy that remains trapped in these regions. So locally, if you have an anticyclone and u squared vanishes, then it's true that the potential will look maybe like, maybe volcano-shaped or something like this. Okay, u squared is 0, so that's maybe this would be the 0 level, but then you also have an anticyclone that's producing this deep with a localized vorticity structure. And if that's the case, particles that are initialized here with 0 momentum, so 0 velocity, if the potential is axisymmetric, they will just go back and forth in this potential well and remain trapped there. Okay, so these small regions are regions where ergodicity breaks down. The particles are trapped in this very local potential, and they will oscillate well, we cooked up a model where this potential is locally axisymmetric, and in that case, all the classical particles just oscillate radially, and you can compute their PDF because it's just 1D radial motion in a given potential. Okay? So we tried to refine the prediction because we were a bit unhappy just predicting that this would be 1. This seems a bit rough. And so that's what we got. This is a way to refine this ergodic prediction, taking into account the distribution of E0, which in fact we also approximated using a central limit theorem because it led to a closed form. It's unnecessary, but it was a nice form. So that's the blue region. So again, they're compatible with the ergodic approach. And now these red dots here are what you compute by extracting the local potential here and computing the 1D motion of these particles that would be trapped and just adding the PDFs in these two anticyclones. Okay, so this is clearly less rigorous or less of a method, but that's what we did. Okay. So we can predict all these time-averaged, I've said all this, all these time-averaged statistics, and now from this I'd like to, so I've shown you how we can compute various time-averaged statistics for weak gamma and for strong gamma, and now I'd like to conclude on this part by going back to the concentration of near-inertial waves in anticyclones. Okay, so why is it maximum at intermediate values of gamma? What have we understood from these asymptotic expansions? Okay, so I'm going to introduce this metric sigma here, which measures, to what extent the near-inertial wave kinetic energy is concentrated in anticyclones. Okay, to do this, I'm multiplying m squared by minus the vorticity and time averaging. So this will be positive if the energy is predominantly in anticyclonic regions. Okay, will be negative if it's predominantly in cyclonic regions. And I'm divided by the absolute value, by the average, where I consider the absolute value of the vorticity, so that, this quantity is between -1 and 1. It's +1 if all the kinetic energy is contained in cyclonic regions, in anticyclonic regions of the background flow. And it's -1 if all the kinetic energy is contained in cyclonic regions of the background flow. Okay?
Not quite a correlation coefficient. So why did you divide? I mean, normally we divide by the product of the RMS.
Yeah, but then, I wanted something to be between -1 and 1, because it's sometimes hard to make sense of the magnitude, and the vorticity PDF can be a bit funny, so I don't know. It's not too bad. We took that from a paper by Xie and Zhang, maybe. They used this, so we took this one, not sure. Yeah. Maybe you should look just at the correlation coefficient. So that's the numerics, okay? So Alexandre ran, sweep in gamma, going from very low values to very large values. The numerical data are these diamonds here. And the theory for low gamma, this is the expansion that we push to second order in low gamma. And this is the result of the refined ergodic prediction that I've shown you. So we can see several things. First of all, sigma is always positive, regardless of gamma. So indeed, there's a preferential concentration of the near-inertial wave energy in anticyclones. However, it's a very weak effect for both weak gamma and large gamma, with sigma going to 0, to 0 here, to small value in that limit. And that seems to be well captured, by the two asymptotic theories in the two limits. Okay, so weak gamma to second order, and this is the ergodic theory plus trapping, which I've shown you. And here, I'm not sure if I should show that to mathematicians, but it's a bit frustrating that you can capture the two limits so accurately, but of course here for gamma equals 1, you have no asymptotic expansion that holds, and to some extent it's the regime, that's where the phenomenon takes place. So we just said, well, maybe we can just cook up a Padé approximant, a 2-point Padé approximant that would coincide with this expansion for weak gamma and coincide with this expansion for large gamma. And that's what we got. So we were quite happy with it. It gives you a fairly accurate uniform approximation over the whole range of gamma. I have no clue, whether you control the error you're making by using such a Padé approximant, but just it seems to be doing quite well. Okay, And so the conclusion is that indeed, now we have an explanation as to why the preferential concentration is maximum for intermediate gamma, because, well, it's close to 0 in both limits, and we predict that it should increase as we go to gamma approximately equal to 1. And if we want quantitative predictions, we can do this Pade approximate thing. Okay? So that's what's written in this summary slide here. Okay, so 2 expansions, a standard expansion in weak flow amplitude, kind of similar to the standard quantum mechanics weak potential expansion. And then the fast flow regime, here it's the classical limit, and I think we can use statistical mechanics to make quantitative predictions. It was pretty good for sigma, at least, and for the spatial distributions. And then, that gives us a way to explain preferential concentration in anticyclones only for intermediate values of gamma. Okay? Yeah?
By curiosity, do you have any quantification of the values of gamma in different regions of the ocean? To understand the oceanic, typical oceanic conditions in which would be.
Yeah, that's a good point. It depends if you're a fan of this model or not. I think honest values are probably between 0.2 and 5. Okay, this is the typical range that would be reasonable. Locally, you can probably find extreme values, 10 to the minus 1 to 10. In fact, in a fully vertical ocean, continuous vertical direction, there's a version of this model where every vertical mode of the wave field would come up with its own value of gamma. In that case, some modes will have very large gamma or very low gamma, but it's not clear that they contain a significant fraction of the energy of the whole field. Okay?
You mean with continuous vertical?
Yes. Yeah. Yeah. Here it's a 2-layer model, but you can do the continuous version of that. Okay? How much time do I have? All right. So now I'd like to switch to something different. And we've discussed near-inertial waves over a background flow. And I was hoping in the remaining time I could tell you about something different, which is inertia-gravity, internal gravity waves in a weak background flow, because the phenomenology is quite different from what we've just said. And now, I'll be discussing stuff that is not my work at all, but which I think is interesting, and connected both to this problem to some extent, and also to the problem of turbulent cascades, and maybe it will provide an introduction to the turbulent cascades of wave turbulence in George's lectures. Okay? All right. So here, I want to discuss internal gravity waves over background flow. So and over that will be a weak background flow. And I want to discuss diffusion in wave number space. And that's work in this context due to Kafiabat, Sava, and Van Est fairly recently, with then further contributions by several people. So I'll be considering a steady background flow. Again, now it's 3-dimensional. I will be considering a 3D periodic domain. And I will now be considering linear, small scale, internal gravity waves. Okay, and by small scale, I mean a scale much smaller than the typical scale of the background flow, which is the inhomogeneity of the system. And so I will be in the WKB / ray tracing limit. Okay, so to describe waves in the ray tracing limits, it's very close to the classical mechanics limit that we discussed. So the waves will be considered to be wave packets with a position x of t and a wave vector k of t. Okay, and you're going to write the dispersion relation omega of xk as the intrinsic dispersion relations. That's the dispersion relation in the absence of a background flow. Intrinsic dispersion relation. And then you have Doppler shift due to the background flow. Okay, so it's u to the function of x dot k. So that's the Doppler shifted.
This background flow conserves the classification.
Yeah. Yeah. You can have a balanced background flow that conserve. Yes, it could be, for instance, I don't know, you can picture a horizontal flow, horizontal components, but function of z, for instance.
No vertical component.
Yeah.
It's a steady flow, but there's no vertical.
Horizontal.
Yeah, horizontal independent of z, for instance. Yeah, that's one way too. Okay. So this is the dispersion relation with the action of the background flow. That's just a Doppler shift term. And then the ray tracing equations, and I'm not going to show that, they're the Hamilton equations for position and wave number that plays the role of momentum using this as the Hamiltonian. Okay, so x dot will be d omega dk. Well, this is to be understood component-wise. And k dot is minus d omega dx. Okay? So again, we can write the Liouville equation, maybe. So we're going to consider, again, the phase space xk. We're going to consider a local density A of x, k, and t of wave action, okay, which is the conserved quantity for these wave packets in moving media. So they move around, conserving their amount of wave action, if you wish. So this density here will be conserved in phase space, okay, which means that we're going to write that dt of A, conservation equation, plus the divergence in phase space, so that's a divergence with respect to x and k, of A times the velocity in phase space, which is d omega dk minus d omega dx equals 0, okay? But of course, this thing here is divergence free, okay? If I take dx of this minus dk of plus dk of this with the minus, I get 0. So in fact, I can expand this simply as an advection term, d omega dk minus d omega dx dot the gradient in x k space of A. Okay? So that's Liouville equation. And maybe I'm going to write it as dt of A. I have d omega dk dot grad A, grad in space. D omega dk is Cg hat, which is just a function of k, plus u of x. Okay, this is the intrinsic group velocity. Just take the derivative of the standard dispersion relation without background flow. Dot gradient in x of A. And then you have this other term, minus d omega dx dot grad k of A. Okay, that's 0. And this is the Liouville equation. All right. And so now we're going to consider an ensemble of waves with the same frequency omega 0. Okay? And we're going to consider internal gravity waves with the same frequency omega 0. So that's something you can do experimentally, for instance. Pierre Cortet has done it. Okay, so you have a bunch of cylinders that oscillate in a tank at a constant frequency, and you're going to drive a complicated wave field, but if it's in the linear regime, all the waves will be at frequency omega 0. And if Pierre drove also a mean flow in the tank, he could maybe see something like that, the interaction of these waves with the background flow. Okay? So now just, you know, the dispersion relation of internal gravity waves is omega 0 equals n k perpendicular over k, which is also n sine theta, where this is the vertical, that's k, and this is the angle theta. Okay, and so what that means is that, well, I've just done it here, but basically in k space, these waves, they lie on a cone. Okay, so here is kz, we have kx, we have ky. And the important thing about this cone is that it's, you know, it's an infinite surface, right? So this thing here, it's an infinite surface. So it will be an infinite region of space, of phase space. And so as you let the system evolve, as opposed to the near-inertial waves, the system will never reach thermal equilibrium. There's no way it's going to uniformly populate this surface because it's infinite, okay? So instead, the waves will be transferred to higher and higher k in a cascading fashion, but you will never be able to reach thermal equilibrium, okay? So this is always out of equilibrium. Okay, just to make connection with the previous near-inertial wave problem, you know, near-inertial waves, if the background flow is weak, then the dispersion relation is just omega of k equals k squared. Okay, so you would just have a circle here. Okay, and so it's a finite structure, and so you're going to populate this circle uniformly and see equilibrium. Okay, that would be for near-inertial waves. But for internal gravity waves, that's not going to be the case. Okay? So like I said, what's going to happen instead is that the wave action will be transferred by the background flow to higher and higher k in a cascading fashion, and ideally would like to be able to describe that cascade quantitatively. And that's something you can do provided the background flow is weak. Okay? And so that's what I'd like to discuss now. This diffusive behavior in wave number space. And the goal is basically to try to solve this Liouville equation. It's time for me to use another board. So we consider a background flow, a slow background flow, meaning that U will be much less than the typical group velocity of the waves. Okay, so it's weak as compared to the group velocity. Okay, and then for a general wave system, on a generic wave system, Liouville equation here. So yeah, dt of A plus U plus CG hat dot grad A. And then this minus d omega dx is only this thing depends on x. So it's minus dxi of uj kj dki of A equals 0. Okay? And now, because I'm running out of time, the way I'm going to write that the flow is slow is just wherever I have U, I'm going to write this as CG hat plus epsilon U. Okay, so I'm going to change notation slightly, where epsilon is much smaller than 1, that's a bookkeeping parameter, and this is a scaled amplitude. Scaled background flow. Okay, so that its typical value is order 1, and I have a small epsilon here, so I can keep track of the epsilons. Okay, and if I do this, I will be solving the same equation with an epsilon everywhere. Well, there's a U, there will be an epsilon here, and I will be having an epsilon here. Okay? And I'm going to solve that using an expansion in epsilon. Okay? So I'm going to look for a solution under the following form. So the ansatz will be that A will be some lowest order capital A of K and a slow time capital T, plus a small correction A tilde, which is a function of X, T, K, and slow time. Okay, maybe there should be a K like that. So what this means is that basically in the absence, the background flow is weak, so what the wave packets are doing is that they're just shooting through the domain at their group velocity. Super fast, they're almost not deflected by the background flow, just only slightly. So through this process, in fact, they're going to have uniform density over the domain and depend only on wave number k in phase space, the action density. But then there's a small correction here, which are the fluctuations and the small remaining dependent part in X. And so I will also define a space average. I will define an average over the fast time t. T. And I will demand that the average of A tilde over space be 0. So I also need to define the slow time variable here, and capital T will be epsilon squared times little t. Okay? Why epsilon squared? Well, because eventually we would like to get diffusion in wave number space for this dominant contribution here, and we expect this diffusion coefficient to be quadratic in the amplitude of the background flow, so quadratic in epsilon, and so the evolution will be over time that's quadratic in epsilon. Okay? Let me see if I have something else to say. No, I think that's pretty good. So I want to solve that equation at various orders. So the first thing I'm going to do is compute an evolution equation for this capital A. So I should carry out the expansion, compute a solvability condition, etc. There are shortcuts. So I'm going to average 1 over space and fast time. So I will get d capital T of A here. This velocity here is divergence free, right? Cg is just a function of k, and this is a spatial derivative, so it can just go inside as a divergence, and u is divergence free, so all of that could move inside a divergence. So when I average over space, this is going to be 0. Okay, and so I'm left with this right-hand side contribution, which I evaluate to order epsilon squared, so this will be A tilde here. Okay, so this will be dxi of uj, kj, dki of A tilde. Then I've averaged that over space and over fast time. Okay? Now we're going to look at this equation 1 at order epsilon to get the A tilde that we're going to insert in here to get a closed equation for capital A. Okay, so we need A tilde in terms of capital A. So let's look at this equation to order epsilon. This will be dt of A tilde. To order epsilon, this is grad A tilde. I'm keeping only the CG term. Grad x of A tilde. And on the right-hand side, I'm going to have only the contribution from capital A. dxi of uj, kj, dki of capital A. Okay? So A is now forcing some small A tilde. So the solution for this, you can change variables and show that the solution for A tilde, and I leave that as an exercise maybe. Yeah. This will be the integral from minus infinity to t of the xi uj evaluated at x minus cg hat tau, and then kj dki of a d tau. Okay, so you're integrating this thing, but this is propagation at velocity cg, so you have to evaluate it at x minus cg. Okay, so now we can insert A tilde into this equation here. Okay, so A tilde into 2, and I want to compute the right-hand side, so dt of A will be equal to, let's see, dxi uj, kj, dki of this integral minus infinity to t of dxl um x minus cg tau kj km dkl of A. Okay, so let's see how to simplify this. First of all, this here is independent of k, so I'm going to insert that inside the k derivative. Okay, so it's independent of k. So I guess I'll write an extra step here. dt of A equals kj dki of dxi uj dxl um at x minus cg tau km dkl of A. And I also have a time average on top of all this. Okay, there's a time average here. Okay, and now I'm also going to insert kj in dki, apologies. I'm also going to insert kj in here. Okay, so I can do that provided I remove then dki of kj times this. dki of kj is delta ij, but delta ij times this would be the divergence of u, which is 0. Okay, so you can check that I can just insert that in here. You can expand and check that the remaining term would be 0. Okay, so now dt of A is dki. Okay, so it's starting to look like the divergence of a flux in wave number space. And then I have kj km integral tau equal minus infinity to t of dxi uj at x dxl um at x minus cg tau, and this thing here is space averaged, and then I have a dkl of A, and I'm averaging over time, over fast time t. And hopefully, this is what I was aiming for. I think that's okay. And also, you can check that, this is the long time average of this integral with respect to time. So you can check that this thing here is just equal to 1/2 the integral t equals minus infinity to plus infinity of dxi uj, dxl um, first one at x, second one at x minus cg tau, d tau. Okay, so finally, yes, absolutely. Why would be finite? Well, I guess CG? Oh yeah, this one is non-zero, yes. But these waves, I mean, all these waves have the same wave number, so they all have the same CG, which is non-zero, so that's...
Then you are expressing for line.
The bracket thing, there's a covariance.
Yeah, it's also average over space. So now basically, this is the it's the 2-point correlation function of the velocity gradients. Okay, once you average over space over x, this is the 2-point correlation function between the velocity gradients. And so you assume that this function decays at infinity.
But you are not on the torus. So the infinity.
Yeah, it's a big torus. Yeah, no, that's a good point. How's that? Yeah, okay. Yeah, suddenly I forgot I was on a torus. Yeah, so yeah, that's then yeah. That's all I can say, yeah. I mean, it's easy to run, to design a flow in a 3D periodic domain where this would, have an extent that is small as compared to the domain size. But now, yes, these infinities are questionable. 5 minutes? Yeah, okay. Can I get a bit more? I'll try not to be too late, but yeah. Okay, so dt of A of kj, km, I'm just rewriting this, the integral from minus infinity to plus infinity. Okay, so you can see this is the divergence in k-space of a flux that's proportional to the gradient in k-space of A. So this quantity is a diffusivity in k-space. Okay? So this thing here is the diffusion tensor DIL. Okay, and at this stage, this could be any kind of waves. Okay, so second part, we're going to apply that to internal waves. And again, it's a bunch of internal waves at the same frequency omega 0 for simplicity. And these waves, they have a, so I've drawn the graph here with the angle theta, and so you can check that their group velocity is simply, there's going to be an n over k cos theta e theta. And so now here, in DIL, we're going to change integration variable from tau to r, and r is it's n over k times tau. Okay, the reason I want to do that is that I want this coefficient here to be independent of k, and it only depends on k through the group velocity here. Okay, so if I do that, I'm going to write DIL. It's going to be 1/2 of kj, km, we had those. There's a k that's going to come from the change of variables. There's a 1 over n And then there's the integral from minus infinity to plus infinity of dxi uj dxl um of x minus r cos theta e theta dr. Right, so now I've isolated k. This is independent of k. Okay, so it's some big fourth order tensor G, I, J, L, M that is independent of k. Okay, it has some structure that depends on the structure of the background flow and of theta, but theta is given. The frequency omega 0 is given. I'm going to denote its typical magnitude as G, where the dimension of G, well, we can check what the dimension of G is. Right, this is t minus 1, t, and length, so that's a velocity at length t minus 1. Okay, and so now, all I want to do is show you, predict the cascade of wave action. So based on this, you could assume that there is a source term that's injecting energy at a given wave number k0 and solve this diffusion equation. Or, since I'm running out of time, you can just do it using dimensional analysis. Okay, so you assume the source term injects energy, wave energy, at k0, okay, with the rate at a rate epsilon per unit mass of fluid, right, the standard epsilon of turbulence. And the question is, if I do that, and I look at high k, what will be the spectrum E of k? Okay, defined such that the integral from k equals 0 to infinity of E of k dk equals, I don't know, maybe the velocity variance, just to get the unit of that. This could be k, this could be k perpendicular, this could be kz. We're all on the same cone, so they're just related by sines and cosines of theta. It's really the same spectrum up to these trigonometric factors. Okay, so let's do that dimensionally. We're looking for E of k. Okay, it's going to be solution to this equation with a source term at some k0. So if there's a local cascade, it will depend on epsilon, the rate of the flux in the cascade. It will depend on G, right, which encodes the magnitude of this diffusion coefficient. And then the structure is prescribed by the structure of the background flow. And it will depend on K, obviously. Okay, that's all the parameters that enter my equation. Okay, so that's dimensional analysis. This is L cubed T minus 2. Epsilon is the standard L squared T minus 3 of turbulence. G is a velocity, Lt minus 1. K is an inverse length. At this stage, I have 4 parameters, 2 units. So I'm screwed. I have 2 dimensionless numbers. So you should remember that it's a linear problem. So here the spectrum E of k will be proportional to epsilon. Okay, if there's a source term proportional to epsilon, then the solution will be proportional to epsilon. Or in wave turbulence, you can also remember that, using the standard recipe, the spectrum will be proportional to epsilon times 1 divided by the number of interacting waves minus 1. Diffusion is 1 wave coming in, 1 wave coming out, so it's 2 waves. So this is 2, and we have epsilon to the 1. Okay? So since I know this, I'm going to do dimensional analysis again. So we're going to use E of k over epsilon G and K. This is length minus 1, T minus 1. And now this one is L times T. So we're going to get the spectrum, and I'm going to conclude here. The spectrum will be E of K over epsilon times G K squared equals a constant. And so the spectrum E of K, this constant times epsilon over G K to the minus 2. Again, if you want the constant, you can actually solve the diffusion equation, but basically that gives you a K to the minus 2. And you can do the same thing for the 2D spectrum, E of K per Kz. You would get the same thing with the Dirac function, ensuring that you're lying on the cone that we showed previously. All right, I think I'm going to stop here. And if you have questions.
Take time for one question. Yes, clearly.
For the in the case of gamma large, yes, you say that this is like a classical system and use microcanonical ensemble. Okay, but for the quantum case, why we can we use microcanonical quantum ensemble?
Yeah, that's a very good question, and the answer is challenging, I guess. Even going from an isolated quantum system and trying to understand how it would thermalize in the classical limit is really tricky, and I think it's still an ongoing topic in math and physics. If you start with the quantum mechanical problem, you could say, well, I'm going to diagonalize the Hamiltonian, and then I should conserve the projection of the initial condition onto every one of the eigenmodes. So I don't have just this conserved energy, I have an infinite number of conserved quantities. So I'm not going to solve that issue. I'm just going to say that we're used to also doing statistical physics for classical systems, and we know that recipe, and that's what I use, but I have by no means solved the way through which you go from all these conserved quantities in the quantum mechanical case to thermalization of this isolated system.
Okay.
In the classical limit.
Okay, so let's say thanks Basile again.